Welcome back. In the previous part, we created a high-quality mesh for Venturi tube model. In this part, we will set up the OpenFOAM simulation within Ennova CFD, configure the solver, and post-process the results to understand the flow behavior. While OpenFOAM is a powerful and highly flexible CFD solver, its native workflow can often be complex and time-consuming, especially for new users. Setting up simulations typically requires manual case configuration, file management, and command line operations, which can slow down the overall workflow. Ennova CFD addresses these challenges by providing a user-friendly graphical interface that simplifies the entire process. From geometry handling and meshing to solver setup and post-processing, all steps are integrated into a single, streamlined environment. This significantly reduces setup time, minimizes errors, and allows engineers to focus more on analysis rather than software complexity. By combining the power of OpenFOAM with an efficient and intuitive workflow, Ennova CFD enhances productivity and makes high-quality CFD simulation more accessible. Now, let's move into the OpenFOAM simulation setup within Ennova CFD and walk through the complete workflow, including post-processing and analysis of results. With the mesh already prepared in the previous step, we now move into the simulation setup phase. From the top ribbon, we navigate to the Setup OpenFOAM section. Next, click on the Control Dict. Under the Solver section in the Main tab, we select the preferred OpenFOAM version installed on the system. We then move to the Modules tab and specify the OpenFOAM installation directory. This path can also be obtained from the bash.rc file. Ensure that only the OpenFOAM directory is provided, without including the etc. or bash.rc subdirectories. Back in the Main tab, we set the solver type to compressible and solver as row simple foam. For parallel execution, we use the Scotch method with 12 subdomains. Next, we set the start time to 0, the end time to 300, and the write interval to 10. The rest of the parameters are left unchanged and kept at their default values for this case. Next, we move to the FV Schemes settings from the top ribbon. DDT Schemes is set to steady state. For Geometry Schemes, we select High Aspect Ratio and keep the default values. Next, we move to the FV Solution settings. Here, we set the number of non-orthogonal correctors to 2 to improve solution accuracy. The remaining settings are kept unchanged and left at their default values. Next, we move to the Materials section. Here, we select the default fluid material, air, and keep the remaining properties unchanged. Next, we navigate to the Properties section. The region type is defined as fluid, with air assigned as the working material. We then set the analysis type to RAS and choose K epsilon as the turbulence model for this case. Next, in the Initial Conditions section, we define the velocity in the z direction as 5 meters per second, set the pressure to 101,325 pascals, and the temperature to 300 Kelvin. Next, we move to the boundary conditions. The converging and diverging sections are set as no-slip walls. At the inlet, we apply a fixed total pressure of 101,325 pascals. And at the outlet, a static pressure of 100,000 pascals is specified. All other surfaces are defined as no-slip walls. Next, we move to the Write Dict section. Here, we ensure the required options are selected. We then export the dictionary files by creating a new case directory. This case directory can also be used to run the simulation manually using OpenFOAM in WSL or Linux. In the Run section, select Linux if you are using a Linux system, or choose WSL when running on Windows. Finally, click on Run to start the simulation. A terminal window will open, displaying the simulation progress. The simulation may take some time to complete. In the meantime, you can monitor convergence by plotting the residuals. To do this, use the Residuals Plot option and select the .dat file. Then click on Plot to view the residual graph. You can click Plot periodically to update the graph and monitor convergence as the simulation progresses. The simulation runs for a total of 300 iterations, during which the solution gradually converges. Once the iterations are complete and the residuals have stabilized, the solution process is finished. We can then proceed to post-processing to visualize and analyze the flow behavior within the Venturi tube. Next, to begin post-processing, navigate to the Post-Process tab from the top ribbon. In the Quick Access toolbar, click on the Open File icon and select the post.foam file from the case directory. Click OK, and the simulation results will be loaded into the post-processing environment. To analyze the flow field more effectively, we create a slice plot. From the ribbon, select the Slice Plot option and choose Velocity Magnitude as the color variable. Click Apply to generate the slice, and then hide the surface geometry to focus on the internal flow distribution. As the surface is hidden, the velocity contours on the sliced plane become clearly visible. We can observe that the velocity increases significantly in the converging section, reaching its maximum at the throat. This is due to the reduction in cross-sectional area, which accelerates the flow. Beyond the throat, in the diverging section, the velocity gradually decreases as the flow expands. This behavior clearly demonstrates the Venturi effect, where an increase in velocity corresponds to a drop in pressure. Next, we play the animation, which has been recorded at every 10 iterations, as defined earlier in the right control settings. When we click play, it visualizes how the flow develops and evolves inside the tube throughout the simulation. Next, we enable the vector plot to visualize the flow direction. We set the vector field to velocity and choose velocity magnitude as the color variable to represent the speed of the flow. The vector count is set to 100 to ensure a clear and well-distributed representation across the domain. Click Apply to generate the vector plot. This allows us to observe both the direction and magnitude of the flow, providing deeper insight into how the fluid moves through the converging, throat, and diverging sections of the Venturi tube. You can also animate the vector plot to observe the time evolution of the flow field. As the animation progresses, you can clearly observe how the flow accelerates in the converging section, reaches its peak at the throat, and then decelerates in the diverging section. This dynamic visualization provides a deeper understanding of the flow behavior and development inside the Venturi tube. Next, the contour plots on the sliced plane are modified to visualize different field variables. The contour variable is changed from velocity magnitude to temperature and then to pressure to analyze different flow properties. By switching to temperature, any thermal variations within the flow can be observed, although in this case, the changes remain minimal under steady-state conditions. When visualizing pressure, a clear drop is observed in the converging section, reaching a minimum at the throat. Downstream, in the diverging section, the pressure gradually recovers as the flow decelerates. This behavior confirms the expected pressure-velocity relationship in a Venturi tube. This completes the CFD simulation and analysis of flow through a Venturi tube using OpenFOAM within Ennova CFD. The workflow covered geometry preparation, meshing, solver setup, and post-processing of results. A complete CFD workflow was successfully carried out, from geometry creation to final post-processing. The entire process was executed within a unified environment, taking the model seamlessly from geometry to results. The OpenFOAM setup was streamlined, reducing the typical complexity and manual effort involved. With efficient meshing and simplified solver configuration, the overall workflow became faster and more productive. Integrated post-processing tools provided clear insights into the flow behavior. Overall, Ennova CFD simplified the simulation process while enhancing efficiency and usability. Thank you for watching. For licensing, demos, or support for Ennova CFD, contact us at sales@daysiminnovations.com.